Thanks for the introduction. Thanks for the opportunity to be here. I'm really honored to speak, talk about some mechanical properties. I know we've been focusing primarily on 2D perovskites, and as Rhiannon had mentioned in the introduction, I'm focusing more on 3D. But there are the same types of metrologies apply, and I actually be very interested in continuing discussions with all of you further about characterizing strain in 2D perovskites. So before I get started, I just want to give a big shout out to the team that actually did the work. I like to think of them as superheroes of sorts. I've been really lucky to work with some really amazing folks from my advisor, my PhD advisor and co-advisor, Reiner Dausgaard and Mike McGee, to some former group members at Stanford, Kevin Bush and Adam Prinz, to now some undergraduates at ASU, Carson and Marco. And so with that, I'd like to get started and just mention, first of all, the issues that we have with perovskites as a PV material, which primarily relates to the fact that they're quite unstable, both chemically and mechanically. So here you're seeing actually an image of some delamination occurring after thermal cycling of an encapsulated perovskite device where it generates no photocurrent. We also have shown that the application of tensile stresses when exposed to high humidity or high heat leads to rapid degradation of the in this case it's methylammonium lead iodide from its black phase to a lead iodide based yellow phase, whereas going into compression significantly enhances stability. Now, we think there's actually, I believe there's a link between these mechanical and chemical effects. You can actually quantify this in terms of a mechanical driving force that scales as the square of your film stress. And when that exceeds the material's resistance to fracture, the critical driving force, then you have this degradation and delamination and ultimately device failure. So this plot here shows just that. Logarithmically, we're showing fracture energy against stability on the x-axis. Something like a commercialized technology like silicon is quite mechanically robust and of course stable to 20-year lifetimes. Formerly competing organic materials, which we all are pretty familiar with, did not make it to market, and that was largely because they are unstable and mechanically also quite fragile. Now, the big challenge with perovskites is they happen to be the most mechanically fragile and unstable of any PV technology that's been studied. And so there are real challenges here when it comes to the fracture side of things. Now, the other aspect that's particularly concerning is that these perovskites develop large tensile strains or stresses from processing. And again, here we're focusing on a 3D system, but of a thin film, but it's the analog is completely identical for 2D materials. So perovskites, both 3D and 2D, have very high thermal expansion coefficients relative to the stiff glass or silicon substrates upon which they're typically produced. And so the mechanism for stress developing is that you would have initially a liquid that doesn't support any stresses or strains, and so that's all your precursor mixture. And then if you're using something like spin coating, you would generally have a phase where you would quench, and then you would anneal at a temperature of say around 100 Celsius, and that's the temperature at which the perovskite forms, and a constraint occurs between the film and the substrate. And then upon cooling, the perovskite wants to contract significantly, but it's constrained in both directions. And so this is what leads to these large tensile biaxial strains. So in this talk, I'm going to go through some of the methods of how we measure these stresses, talk about the primary mechanism, which I've already hinted at, and then some approaches for how we can reduce stresses. So the primary method that we use is actually a curvature-based approach. And the idea is quite simple. It's that after you apply a film, and if there's any amount of stress between the film and the substrate, it will cause a curvature in the substrate or a bending, either upwards or downwards. And what we do is we have a laser that scans over the back of the substrate and looks at the and is able to then calculate a deflection. And we can map this deflection to a curvature, and then knowing the elastic properties of our substrate and the thickness of our film, we can back out the film stress. Now, it's important to note we actually don't need to know anything about the properties of the film elastically. So that's why when I say this is even though we're talking about 3D perovskites, it's extremely relevant to 2D layers as well, because all you need to know is the thickness of the perovskite film itself, and the same exact approach applies. And what we did to actually measure the this is, by the way, is also called the Stoney equation. It's about a 100-year-old equation. And what we did is we looked at different annealing temperatures and measured these film stresses, and noticed a linear pattern of increasing stresses with higher annealing temperatures. We are actually able to model this based on the thermal expansion mismatch between the substrate and the perovskite, and then the change in temperature, which is the cooling from the annealing temperature back to room temperature. And we noticed that our model was quite accurate in capturing the stresses that develop in these perovskite films. Now, more recently, we've actually been able to measure stresses in situ, and this is an exciting technique that uses the same exact mechanical principles, except instead of looking at a change in curvature, we look at a deflection of a cantilever that will bend upwards or downwards. And this doesn't rely on a laser, and it actually just relies on a capacitive measurement. So it's very portable, and it can be done while exposing perovskites to different thermal or environmental stresses. And one aspect that we were studying in this work is that when you shine light once on illumination, the perovskite heats up higher than the glass substrate itself. And that would actually result in expansion. And so we were able to actually characterize that we could measure these decreases in stresses because the perovskite is expanding under this light application. And we did cycles of light and dark and showed that this was highly repeatable. And we mapped it to a thermal expansion by replacing the light with heat, so heated air that was at the same temperature, and saw the exact same magnitude of the effect and kinetics as well. So this shows, it's hinting at, or is really indicating that it is indeed thermal expansion that dominates, or the mismatch in thermal expansion that really dominates these stresses. And so as we look at this equation, we can get an idea that either decreasing our substrate to match or increasing our substrate thermal expansion to match our perovskite, or decreasing our formation temperature are both effective ways of mitigating stress. Also, from the strain can be measured by looking at the changes in the lattice spacing. This is just a third and final approach for measurements. And this is done using what's called the sine squared psi method, where basically the film, you use a grazing incidence, and then you have a rotation in the film, and you're able to then back out how the lattice vector changes. And there's actually a linear relationship between the d spacing and the sine squared of this angle psi. And so this shows our linear relationship, where when you measure the slope, you're actually able to back out this lattice spacing. And from that, you can calculate a stress. And so we've done that, and we confirm the same trends. This time we were on glass instead of on silicon. So with a slightly higher thermal expansion coefficient, the magnitude of the stresses are reduced. So now I'd like to talk to you and continue to focus kind of on the fact that we've identified this thermal mechanism for film stress, and how we can mitigate this using different approaches. And the first was that it was actually the idea that the formation temperature is what's critical. The fact that the perovskite attaches to the substrate and is constrained at the high temperature. So rather than having to reduce the annealing temperature, which can actually result in lower quality films and different properties that are less desirable from an electronic point of view, we instead decided to use an alternative approach where we quench the perovskite fully in an anti-solvent bath. In this case, we use diethyl ether immediately after spin coating. And so in this case, the constraint would be that the perovskite attaches to the substrate at room temperature, and then we annealed to remove any of the anti-solvent and form our perovskite. And the idea is that in this case, there should be no residual stresses because the perovskite attached at room temperature, because it will swell and then contract together with the substrate upon annealing. And we actually saw exactly that. In this case, we were looking at different annealing temperatures, and in all cases, the stresses were almost identically zero, where we would have expected if the based on previous annealing temperatures, if the formation occurred and at higher temperatures, we would have expected a tensile stress. So this was a promising approach. The other comment I want to make, that's because mechanics overall are often misunderstood in the literature, is that there are, and the idea that these thin film devices are going to have a number of different layers, is that we probed the effect of underlying charge transport layers and saw no major effect whether we used no transport layer. In this case, we're looking at triple cation just on silicon, or if we used an organic polytriarylamine whole transport layer, or if we used a nickel oxide layer. There's some spread here, but the trend is very similar. And so this is just an important indication that because we're not dealing with epitaxial growth situations that or lattice matching between layers, the effect of the contribution of thermal expansion from any other layers, both either underlying or overlying transport layers, should not have an effect compared to the substrate. The substrate should dominate the residual stresses that form after processing. And this is important to note because there's been some kind of misunderstanding in the literature is talking about controlling stresses based on modifying the charge transport layers. And at least from a thermal expansion perspective, that is simply not the case. It could be related to other mechanisms, but very unlikely to be from thermal expansion. So now we can talk about some ways that we can actually reduce the film stress. And we had discussed already the idea of using thermal substrates that have higher thermal expansion coefficients. In this case, we replaced our silicon with a plastic-based or polymer polycarbonate substrate, which is much more closely matched to perovskite thermal expansion. It brought down the film stress significantly, and also we noticed that under accelerated high heat aging and we observed that the film was much more stable over the course of this was 100 hours at 85 Celsius. The other approach would be to actually change the kinetics of formation so that you can have, we discussed about how forming in a bath at low temperature can allow the perovskite to attach at room temperature. In this case, we used an alternative approach that was an open air process method where we actually spray coated the perovskite and used an open air plasma system to then crystallize the perovskite very, very quickly. So that this prevents as much heating from happening because it's a very fast process, and the plasma contains reactive species and ions that enable more rapid crystallization. And so we did this in the synchrotron, where we did some in situ measurements, and we observed that this is a waterfall plot showing time on the y-axis, that after the plasma goes over, we don't see any crystallinity obviously until the plasma comes across, and once the plasma is exposed, we see these crystalline peaks that occur almost instantly. And if we zoom in on this plasma exposure, we see that in less than 1 second, we have conversion to the perovskite. And our hypothesis was that this would greatly reduce the thermal expansion and the resulting stresses. And we indeed, we actually were able to verify that and see for a range of compositions, in this case, different cesium contents in our perovskite, that the plasma cured samples had lower film stresses. Now, the final approach is one that we've been looking at more recently, and this is something that was hinted at and was discussed earlier in the session by Adam and others in terms of basically applying a pseudo compression, and this was through actual ion exchange. So rather than, it was discussed earlier about cations, but in this work, we're actually interested in looking at anion exchange, where after formation, the idea is that we start with a lead bromide based perovskite, and then we perform a halide exchange to replace the bromine with iodine, which has a markedly larger bond length and should cause the lattice to expand significantly enough to overcome the residual, any sort of tensile stresses, which, by the way, we're looking at on the order of about 50 or so megapascals. It was mentioned in the discussions earlier that we could get up to even, the gigapascal range, depending on what substitutions are used. In this case, for this type of transition, we would expect something like on the order of 100 or so megapascals, so a little bit less, but still enough to overcome any residual tensile stress. And so our initial trial at this was to take basically an iodide-rich film and a bromide film, and then put them in direct contact with one another and heat them up to then promote this interdiffusion. And what we found is that this was indeed effective. You start with a dark iodide, you end up with a bromide-based perovskite, and then the opposite occurs. And in this case, this is where we would anticipate there would actually be compression occurring from this exchange. However, we kind of had a bit of an oversight in the fact that we didn't realize that the fact that the perovskite itself actually reforms at these high temperatures. And 150 Celsius is actually higher than the initial annealing temperature. So unfortunately, we actually observe an increase in the stress based on the fact that the perovskite reforms at that high temperature, and then you have all this thermal expansion as it cools back down to room temperature. So this was actually corroborated based on lower stability results too. We actually tried to enhance this interdiffusion process by putting different weights on top of the stack, and then looking to see how. So we did, after initially we have our iodide and bromide, and then we, in all cases here, this is after our annealing, our 150 C for an hour, or for 12 hours, and you can see on the left here and on the right we have some phase mixtures, but the challenge is, because there's higher stresses after they're aged at high temperatures, you can see that they all start to degrade more clearly, much more noticeably than the controls even. So this is showing that approach was not really effective. And so the natural response, or the natural idea, is to then try to accomplish this halide exchange without the heating step. And so that's actually something we've been looking at very recently, is taking a bromide perovskite and then actually exposing to a vapor that contains iodine in it, and then this can actually be done near room temperature, and we can, over time, with more vapor conversion, we are able to see the transition from the bromide-based perovskite to an iodide-based perovskite. We are getting very close to pure iodide perovskites, and we're hoping now that through this method we'll be able to measure and actually obtain these compressive stresses to increase the overall stability of the system. So with that, I just wanted to kind of overview what we discussed, is that you can use these curvature and diffraction based techniques. We focused on curvature methods for measuring the biaxial stresses that form, that are macro based stresses. There are also work in the literature that talks about micro stresses and nano stresses within grains and such, which could be characterized from diffraction. But we are studying looking at kind of the overall effect on the film itself. And we notice that those macro stresses are really dominated by thermal expansion. That said, though, there are approaches to mitigate this effect, from halide exchange, from formation temperatures, from changing the substrate. And also now there's an interesting area of additives as well, the opportunity to maybe put in additives that could induce compression from processing as well, which is a very early stage effort that's being reported in the literature. And so with that, just would like to thank you for the opportunity to share this work, and look forward to the discussion in the session that follows.